Okay, hey, I'm Felix Domke. I'm doing a talk on Jtag blackbox reverse engineering today. This is a hardware talk. I hope you are not scared away. It looks like, well, the room is more empty than before, but anyway, I appreciate your listening to me. So, Jtag is a topic I worked in my spare time for the last few years, and I finally want to present my findings about what you can do, what you may not have known before. So, the alternative title is The Secret of Jtag. So, yeah, this is a hardware talk, but you should listen anyway, because even if you're a user of some hardware which you think that is secure, you might be interested that a hacker could use Jtag to hack into this device. And you might not even know that this device has Jtag. So even if you're a hardware developer, you probably know that there's a Jtag port on the device, but you might not know what exactly you could do with it beyond of what the manufacturer tells you to do. So this talk, tries to make you aware of what Jtag actually means to you and to security in your hardware. And this is not, what is this not? So this is not a talk on how to revive your bricked hardware using Jtag. There are pretty good resources on that, and like there are other talks, I think, from previous C3s, and there are also online resources. So this is not a talk about how to use some existing software to reflash your router or something. When I tell people that I'm working on Jtag, they always ask me the question like, can I use my Wiggler Jtag interface for doing Jtag stuff? And the question is pretty much like, can I use a PC for doing development? The answer is of course, but you have to know what you're doing. So in the end, you probably have to solder your own Jtag interface, but it's not hard. The physical layer of Jtag is really simple. It's really just a few wires you need to attach to some GPIO pins, and then the rest is software for you. I'm a software person, so I always enjoy if I can do everything in software and don't have to solder that much, because I suck at soldering. So yeah, so let's start. This is part one, the 3 types of developers. As said, I'm a software developer, so this is pretty much my workflow when I do some software development. If I want to write a program, I think about the design a bit, I think about the design a bit more, and then I start implementing it, like hacking some code together, and finally I compile it and I run it, and if it runs, it's fine, and I will deploy the code. And if it doesn't run, well, I spend some time debugging the issues and finding out what's wrong, changing that in my code and recompiling it, and then try it again, right? And this whole steps take like, depending on your project size, several seconds or several minutes, maybe more, maybe less. So it's really a matter of a coffee or something. And the way people do debugging in software project is that hopefully they start with unit tests, so they know that parts of the software is already working and they have their test sets and so on. Then they're probably adding a lot of debug code, like optional debug traces and a lot of debug printf. Printf is actually a pretty popular way to debug programs, and well, I mean, it works great, right? Some people use debuggers and enjoy like messing around with the state of the program while it's executing, or observing memory while it's executing. There are lots of ways to debug software. I think all of you know that. The problem is that the debug code that is added into a program affects performance and the code size. Like if you ever compiled a huge project with symbol information, you know that it can be 10 times as big and even bigger. So before deploying, you have to, or you should, remove the debug code and build a release build of your software. Like you remove all the debug code you added and you remove symbols from the build process. And then you just hope that it still works after you changed the program to not be a debug version anymore. And usually this works fine. I mean, that's what we're usually doing so. Another type of developer is a hardware developer. So, I mean, a lot of us probably already developed hardware, but I'm not so much a hardware programmer, so this is how I think a hardware developer implements his stuff. So first, again, you should think about what you actually want to build, and the design stage might be a bit more extensive than for a software project, depending on the size, of course. Then you start implementing, like drawing schematics and routing the PCB, and if you're happy with it, and you might run some simulations, but you could also just send it to some manufacturing company, and they will build a prototype batch of PCBs, and you get them back. Depending on the project, it costs maybe a few $1,000s, depending on how many components you have, how complicated the setup process is, how many layers your PCB has, and so on. But it usually takes a few weeks until you get back prototype boards. And then you get those prototype boards, switch them on, hope that there's no smoke, and then you will do some measurements, like checking if the voltages are okay, and then you try like doing simple stuff with it, like trying it to boot simple code. And well, you will debug the board, and you will either find that it works as you think it should work, and then you can ship it, or you find some bugs, and you will again try to understand the bugs and change that in the implementation, like fix the schematics or fix the routing or the placement or whatever, and then you do another run, which costs another few $1,000s. It is pretty much okay if you don't need that many revisions of the hardware. So hardware developers add debug stuff too, like they add test ports on their devices, because measuring signals can be pretty hard if all of them are BGA type devices. So you want to route some signals you're interested into dedicated test ports, so you can easily attach your scope or logic analyzer to them. And sometimes you have like different options how to configure something. Like you could have two different power regulators on it, like a linear regulator and a step down, and you could choose between those by populating different parts. So if you think your problem is in the actual power supply, you could try different combinations. And I mean, the good thing about this is if you deploy your product and it fails in the field, you can get it back and repopulate the test headers. So you don't even need to populate the test headers when shipping a project or a product. So that makes it pretty cheap to add test ports. That requires a bit of PCB space, but that's it. So the advantage is you can still debug units you got back when they fail is often enough that hardware designers don't bother in removing all of the debug features, and they're not doing a separate retail build. So usually the revision you get in the store is pretty much the same that has been used for like the last few design stages. There's no separate non-debug version of the board usually. Now, a third type of developer, it gets more and more hardcore, is a silicon developer. I mean, I'm not a silicon developer, so again, this is just how I think silicon developers do their work. They spend a lot of time on the design phase, really like a year or more. Then they start implementing the code, like the HDL code or something. They develop they do a lot of simulations, and when they're finally happy with what they have, they send it to the fab, and they will like build masks and produce some silicon, and you get back the silicon, and then it hopefully works, right? Because the whole test run costs easily $1 million or more, and it takes easily a few months or more. So it's not something you can do just again because you had a stupid error in it. That's why silicon developers do a lot with simulation. They can simulate almost everything. Like if they're designing a CPU, they can probably boot a whole operating system in their simulator. It will take ages, but they can simulate that it will work. And surprisingly often, the final product works in the same way as the simulation. So the simulation tools are pretty good. It's far better than probably what hardware developers have, like PCB developers, because they can never emulate enough of their system that the result is accurate enough. But for silicon developers, because the turnaround is so expensive and takes so much time, people spend a lot of energy to improve simulation. And the largest part of silicon development is actually doing the design validation and developing test sets and all of that. And only a small part is the actual functional implementation. Still, silicon developers add debug functionality, like they add debug switches where they can, you have a register and you can disable certain parts of the chip because you want to try without those and see if an error you have is still present there. They also add a lot of what software developers have printf for. They add a lot of debug trace output, like signals from everywhere on the chip, so they can observe the operation of the chip while it's running. And finally, they have powerful tools like an FIB at their disposal, so they can actually fix their chips after they have been produced to see if a bug fix they invented actually works. And it really needs to be right on the first spin. I mean, that's why they spend so much time in simulation. And well, if it isn't right on the first spin, it definitely needs to be fixed on the second spin, which means that since you prepared that the first spin is already working, the first spin, which is the one you're using to debug it, to really get the fix for the second spin, which means that they have to use the first spin, which was thought to be shipping at some point but didn't work, for debugging. Because if they cannot figure it out on the second spin, they probably run out of money, run out of time because the product obsolete, and well, it really should work in the second spin at last. So you could ask, well, they could just leave their debug stuff in there. I mean, what's the reason to remove debug stuff at all? Because it usually doesn't affect performance. Well, it adds cost to the device because it adds silicon area, which translates to cost per device, but it's usually not that much, so it's okay. Another problem is that hackers can actually use the test functionality in the chip to work around security which might be implemented in the chip. So this is a reason why it would be nice if you could remove the debug functionality, but it's not like in software where you can do a simple recompilation without debug flags or something. In fact, you have to do all the validation again and do yet another spin, which really takes time and money. And you should, or silicon developer ask themselves, is it really worth the 1 million that we remove some debug stuff? I mean, 1 million translated to silicon area is quite a lot. So also it might be an advantage if the debug stuff is still in there, because again, if a device fails in field, you can use that available debug stuff to do a post-mortem analysis and see why the device actually failed. And finally, doing waiver sort, you have to test your silicon if it works and throw away if it doesn't work. And you need some test modes while doing the manufacturing, and you need probably also some test modes while doing the production, I mean the system assembly, when you solder it on the PCB and you want to check if all the solder connections are okay. So this is a small overview about the different types of development and what the turnaround time is. And yeah, there's really a huge difference. So the usual shipping state on software is that there's no debug information embedded. This is a bit different for silicon. Usually the debug stuff is just undocumented. And most chips still have their test mode functionality physically present on the device. That doesn't mean you can immediately use it, but it's still there. And it's usually undocumented because it's meant for production testing, and no silicon manufacturer wants to tell the user how to do waiver sorting, because there might be proprietary algorithms in there, and it's just none of their business. So it's usually undocumented. The problem here is that those test modes are present and can be a huge problem for secure hardware, because you think the hardware you just built is secure because there is no, let's say, a serial port on it or something. But in fact, there's a test mode which you don't know about it because you just have the data sheet from the manufacturer and they don't tell you about the test modes. So you should be aware that some test modes might exist even if you don't know about them, or even if the vendor doesn't talk about them. So what silicon developers are actually debugging is, well, I already talked about it, that they add a lot of debug outputs. They can see what's wrong if something doesn't work. And this is also important. Sometimes it comes from the simulation, so you can, in the simulation it's easy to tap some signals, but sometimes there are even leftovers from simulations in the silicon because they fear of changing anything after simulation, even if it's just removing some registers or something. So usually what they simulate is exactly the same what you get in silicon, even if it doesn't make much sense because it's really just in there for simulation. There are debug switches, and overall, you could all route them to test pads on the silicon and have a huge bed of nails tester. This was done 20 years ago. It was a standard practice that a PCB would go through a bed of nail tester where you would insert the PCB and a lot of nails would attach to test pads, and then you would run some tests. But now this is becoming more and more expensive because silicon area is also constrained by the number of number of I/O pins is constrained by the silicon area, and the logic gets smaller and smaller, but the pads are roughly the same size anymore. So you get much more logic for the area that you could use for one I/O pin. So at some point, somebody thought that, well, maybe we should just add some more logic and less pins. And this was when Jtag was introduced or standardized. Jtag is actually the group that defines some standard, but when I talk about Jtag, it's like MPEG and JPEG. I'm really talking about the standard itself or the implementation of that standard. So it was introduced in the 80s, and it's really popular since maybe the middle of the 90s, maybe a bit earlier. So almost any complex chip you get has a Jtag port these days. Jtag can be thought of a state machine, which allows you to access several scan chains. A scan chain can be thought as a register. Like if you're a software developer and talk to hardware directly, you know that there are like registers where you can set up hardware, like set up clock weights or whatever. And in fact, a scan chain is something very similar to a register. In fact, it's implemented as a serial shift register, so it's a register you can load in a serial manner. And well, we will take a look at this now. As said, the physical layer of Jtag is really simple. You have like 4 and 1 optional I/Os. Like there's a test clock, and all the other pins are synchronous to that test clock. Then you have a test mode select, which allows you to walk through a state machine, through the Jtag state machine. I will talk about this in a few minutes. And you can connect those serial shift registers, those scan chains, between TDI and TDO. So TDI is the input into the serial shift register, and TDO is the output. And if you're supplying a clock, you can clock in data into this register, and you can also read that register out. I think if you have ever opened the hardware, you've probably seen a Jtag connector. So there's no standard pinout for it. So we see a few examples here on how a Jtag connector could look like. It's probably right next to the chip, which is attached to sometimes you don't know the pinout because you don't have the schematics for a device or something. So to find the pinouts, there has been some work by Hunz. He implemented a Jtag finder, which could find Jtag or identify Jtag pin out of a number of candidate pins. The question is, how do you find candidate pins? Well, sometimes it's easy. Sometimes there's a connector, maybe even labeled Jtag or something. Maybe often there's no connector. Maybe they're just test pads which are numbered and not like sorted in any manner. So what you should do to find candidate pins is to either look at the data sheet for the chip if you have it, or in similar devices where you have the schematics for and which use the same chip, and see what pull up and pull down requirements there are for the Jtag port. There are usually requirements like you have to pull up the test reset pin with like 1K. So the data sheet of the chip says you have to pull up the T reset with 1K, and you have to pull down TDI with 10K, for example. And usually the hardware designer just used that and don't re-implement the pulling scheme. So they really just use the values the vendor suggested to them. So if you find some pins which had this right pull up, pull down requirements, like you measure the resistors on the board and say, oh, it matches more or less what I've seen in this other board near the Jtag connector, then it's a great indication that those are actually Jtag pins. And now the Jtag finder will be able to brute force the combination of pin and find which actual permutations of the pin is the right one. So you can find those pins and you solve the physical layer. A scan chain here's a logical representation of a scan chain. It's usually implemented as flip-flops in hardware, but it works like that way. You have the TDI, the test data input, which is a Jtag pin, connected to the input of the most significant bit, and the least significant bit is connected to the TDO. And whenever you clock through, whenever you apply a rising edge on TCK, the register will shift one to the right, and it will shift in the data from TDI and shift out the data to TDO. And here we want to scan in the value 10000, and previously it was all 1. So whenever you shift a scan chain, you will read and write. There's no way to just read or just write. You will always do both. So you replace the content. So we will tick through the individual cycles, and we see that we were able to replace the content of the scan chain with the new content we want to scan in, and we have been able to read out the old content of the scan chain. So that's the basic operation, how you operate a scan chain. The question is, there are many scan chains in a device, and obviously we need to have some way to select them. So this is where the TMS pin comes. This is a Jtag state machine. It might be a bit hard to understand at first, but it's really simple. So depending on the state on TMS, it's either high or low. You will walk the blue or the red lines. So you start in test logic reset, the thing on the top left, for example. And if you want to stay in test logic reset, you need to have TMS to high and do a clock cycle. Or you could move on to the run test idle state by doing by pulling TMS to low and then doing a clock cycle. And if we want to actually access a scan chain, we have to walk a path on this. I will show you an example. So say we want to shift in something into the IR register. I will talk about this soon. The IR is one of the scan chains that can be selected using that state machine. Then we need to run the path through on the right side, basically. We'll see this in a second. So we will first keep TMS low and issue a clock cycle. So we will move on to the run test idle state. And then we will need a clock cycle with TMS being high. So we are to select DR scan, then select IR scan. Now we want to not walk to test logic reset again, but we want to go to capture IR. So we want to move down. So we need to have a clock cycle where TMS is low. So we do this, and we get into the shift IR stage. And this is where the actual shift register is connected between TDI and TDO. And now we're doing what we saw on the previous slide, where we just scan in 2 bits of data. I simplified this by just scanning in 2 bits here. We are keeping TMS low if we have more data to scan, like on the first cycle. And on the second cycle, we pull TMS to high, so because we want to leave that state, we're going over exit, update, and then we're in run test idle again, and we have successfully scanned in 2 bits into the IR. So you can see here that there are 2 distinct paths. There are 2 registers you can access using the state machine, the DR and the IR. The IR is called instruction register, and the DR is called data register. The problem is the chip has a large number of scan chains, like it can be easily in the range of hundreds, and there's no separate path for each of those in the state machine. So they are indirectly accessed. So the instruction register is actually a pointer, and the DR is a symbolic name for the currently selected scan chain. So you can select a scan chain using the instruction register and then operate on it using the data register path we've seen on the left side in the state diagram. It's important here to know that each scan chain can have a different length, from 1 bit or even from 0 bits to a huge number of bits. So it's not like in a CPU where all registers are like 32 or 8-bit in size. Each of those scan chains can have a different length. So the instruction register is as I said, the register used to select the data register. And the instruction register is usually like 4 to 32 bits in length. This is implementation specific, so every chip has a different IR length. And for example, if the IR is 4-bit, it allows you to select 16 different data registers. If it's 32 bits, well, a chip doesn't implement 4 billion scan chains, so lots of them are usually not implemented, but they have for other reasons a long IR, maybe because they wanted to align the numbers in some way or have some special bits or whatever. So there are some scan chains which are more or less standard. Like the instruction register is defined in the standard what it does. The length is not defined. There's one register which is called ID code, which is pretty cool. Not all chips implement this. It's an optional instruction or an optional index. If but most chips do implement that, and it's a 32-bit scan chain you can select, and it's read-only, so if you scan in new content, it will just be ignored. And the data you scan out is a 32-bit value, which is a vendor ID and a product ID. So there's a defined list of vendor IDs, and you can identify a chip using that. The problem is the value to select, the value to write into the instruction register to read the ID code registers is not defined in the Jtag standard, but defined is a trick how to access it anyway. You have to go through the test logic reset, the state in the very top left, which is usually just used as the reset state of some Jtag state machine. And if you, all the time you go through this, it will load the ID code instruction into the instruction register, so all you have to do is to scan out the data register and read the ID code. And you don't even need to know what the proper value for the instruction register actually is. So this is kind of a trick. And this is pretty cool because we can identify most chips with those, especially if you have a board where you have the Jtag pin out, but you don't know what's actually attached to it. You can run a scan to check the ID code and probably look it up to find what chip this actually is. Or at last, which vendor it is, because that's standardized. Another very popular instruction, which is actually standardized in the Jtag standard, is the bypass instruction. It is, if you write the instruction register with all ones, you always get the bypass instruction. The bypass instruction is a single bit register which doesn't have any other functionality or something. It's used to daisy chain multiple chips in a Jtag chain. So you can have multiple chips daisy chain to each other. It works by putting TMS and TCK and TReset in parallel to each chip, and then daisy chaining the data line through them, like I showed here. Because they're daisy chained, the Jtag state machine is synchronous on all of those chips. So all of those chips are in the same state. So if you scan in the instruction register on one chip, all other chips will be in the scan IR state as well. So they will, basically this means that whatever you see on TDI and TDO is basically all currently selected register chained together. And this is great because you can tell each chip a different instruction register, which is useful because there might be different types of chip in that chain, and you have to give each chip an own IR value. But you need something of a knob, because if you want to do some interesting operation on one chip, you don't want to do something in parallel on the next chip. So what you're doing is you're putting all the other chips in this bypass instruction, and they will just delay TDI to TDO by one cycle, but you can filter that out afterwards. So this is the way the bypass instruction is mostly used for daisy chaining chips. Another classic example, I think some of you might have heard about this, is the boundary scan mode. This is actually what Jtag was designed for first. It is a way where you can control I/O pins of a chip disconnected from their internal functionality. So typically you have a huge chain, like several hundred bits, which you can select using the instruction register. And you typically have 1 to 3 or something bits per I/O pin. And boundary scan is actually often documented because it's something the manufacturers use in their factories to test the PCB. So you have 2 chips in boundary scan mode, and then you toggle some I/O lines and check if the other chip sees that, and then you know that the electrical connection is okay. So this is called boundary scan because there's between each logical function, like the logic in the chip and the actual physical pin, a small boundary cell will be added. And the boundary cell they are chained together in the boundary scan chain, which you can select over Jtag. And for example, for an input cell, you can probably capture the pin data to read what's physically present on the chip. And sometimes you can override what the internal logic sees. And this is already an interesting thing because, for example, if a hardware designer was clever and thought, oh well, I don't want the hacker to be able to access this USB port, which this chip offers, but we don't want the hacker to have access to that. So, well, a USB is a bad example, I'm sorry. Like an I2C bus, which might be unused. You can use boundary scan to actually override the actual I/O, the actual logic functionality inside the chip without touching the physical package of the physical ball at all, because it might be BGA and buried under some other traces or something. And you can use boundary scan to modify what the chip sees without even touching the physical pin. So this is just something you need to be aware of if you hide pins by just not routing them. They might be accessible over boundary scan. Usually it's used for board level tests, as I explained. So. And then there are a lot of implementation-specific change, and they are usually not documented at all. So each chip vendor is free to do whatever he wants in the IR space, because if he just does not document those, nobody will ever use them, so they can use whatever they want. And it's now interesting if we come across an implementation-specific chain and we don't know what it is, that we need to gain as much information as possible about it, because it might be something a hacker could use to hack your system. For example, we will show later how we find out what change actually exists on a chip. So if you see that there's an implementation-specific chain, you have a scan chain with some bits and you don't know what they're doing, you have to observe. You can observe them. For example, if the CPU boots up and configures different peripherals in the chip, you can see that, for example, if some of the unknown bits in that scan chain toggle as soon as the CPU does initialize the memory controller or something, then you know that this bit is probably related to the memory controller, or any other peripherals. Sometimes, if you're lucky, you actually own the code running on the device. For example, if it's your device, you can run code on it. You hopefully can run code on it. And you can try to match up the registers you see with what you see from the CPU, because if you, for example, from the CPU see a register to configure the serial port, and you change some bit there, and you see on the Jtag chain, the bit chain, an unknown bit changes as well, you might have found the Jtag way to access that functionality. And it's interesting because you can map the Jtag functionality to what you know or what you already know about the chip. Like if you already know about how you can access it from the CPU side, you can figure out how to access it from the Jtag side and access it also on a system where you don't have control from the CPU side. So the unimplemented instructions are usually implemented in one of those three ways. One common way is to just treat them as bypass, so you just use this one bit cell which hasn't functionality. This is one way how unimplemented instructions behave. Another way is that TDI and TDO are connected directly without a delay or without a flip-flop in between. The problem with this is that the propagation delays of the chips add up, and if you have a huge scan chain with several 10 chips or something, you get delays because the TDI has to enter each chip and leave each chip, so you get a lot of you get delays, and you can't use your Jtag port as fast as you want. So that's why usually the bypass cell is used, because it doesn't affect the timing, except that you need one more clock cycle. Another way is that unimplemented instruction behave like TDO is always connected to a 0, so there's no shift register anymore. You can shift as many bits into TDI, but they will never come out of TDO. So this is the third method how unimplemented instructions might be implemented. Sometimes you can read back the instruction register, and some bits will be modified when you read it back compared to what you have written in before. And you will see that some bits might flip if the instruction was invalid or something, so there's like status bits. You have to check your own chip and just play around with it and see what happens if you write that instructions, what comes out of the instruction register again, and try to find a way to identify unimplemented instructions, because your instruction space will be huge, like 32-bit, and you have to filter out all the unimplemented functions first. And usually you will have much less instructions after that. So each scan chain, and that's true for the instruction register and all of the addressable data registers, has some distinct properties. Like it has a length, like each register can have a different length, from 0 to whatever, several hundreds to 1,000 bits. And each of those bits might have a distinct property in the sense that, for example, some bits are read-write, so you can scan in new data and it will survive if you read it out again. Some bits are like directly connected to some hardware functions, and you cannot overwrite them. Like they behave like a read-only bit, so they get updated to their hardware state every time you enter this capture IR state, which is part of the scan chain. And one important thing here is that even though we read the data into the shift registers in a serial way, the update is always atomic. So you shift in the data, and all the bits change while shifting because you shift them in, and they won't get effective until you enter this update state, which is next to the scan state. So they will get effective only after you leave the scan state. So you have an atomic update and atomic capture for all of the scan chains. So you don't need to worry about shifting in stuff too slow or something. If you want to find out the length of a register, well, we assume that the register is already connected between TDI and TDO, so you already went the proper path in the state diagram. And the algorithm is simple. You just clock in a huge number of zeros, more than you think the size of the registers will be, some several thousand maybe. And then you clock in a single one, and then you clock until you see that one appearing on TDO, because it propagates through the shift register until it reaches TDO. And this can be applied to both the instruction register as well as to any data register. So here's the example. So this might be the default content of the shift registers, some unknown values maybe. And you flood it with zeros, and then you shift in a single one, and then you record each bit coming out of TDO, and you're doing that sometimes, and the one propagates to the register, and at some point it reaches TDO. And then you know that the shift register is 5 bits long. So this is how you can determine the length of any unknown register. This is very important, because when you have an unknown chip or a chip you want to find out more about the test modes, the first thing you should do is to find out the instruction register length. So you apply the algorithm I just showed you while walking the instruction register path in the state machine, and you can find out the instruction register length. And then for each possible instruction register, you write that value into the instruction register and do the same length determining algorithm on the data register. So you can build a map of the Jtag space this way. And then you should, if you have done that, you should find out more about the actual bits. Like if you see a register which is like 4 bits, you should try to figure out what those 4 bits actually are. So you might want to read them and see if, or to rewrite them, to toggle them and see if their value changes. And it's very much like registers in a microcontroller, where each bits have a different property. Some are clear only, like you have to write a 1 to actually clear it to 0, like an interrupt status register or something. Some are read-write, some are read-only. Just experiment with the individual bits. And I have some tools written for that automatically try to determine as much as possible, but ultimately you have to try it yourself by manually putting content into interesting registers and see what actually happens if you read them out. So now that we understand Jtag, we are actually in part 3. We are under control of, we don't even know what it actually is. So here's an example. I've mapped a chip. I don't want to name it, but it really doesn't matter. This technique works on many, many chips. So I mapped some chip I had lying around, and it had a 5-bit instruction register. I found that out using the length algorithm. It didn't have an ID code, actually, which is interesting, because most chips have that, and that chip, it was the first chip actually I've seen that didn't have an ID code implemented. You see here that there are 32 possible combinations, of course, for the instruction register. We see that instruction 31, that's the one in the bottom right, has a length of 1. So the number is the length of the actual register as found out by my algorithm. And we expect the bypass register to be at the all-1 IR value, which is 31. And yeah, there it is. We see the bypass instruction at that location. And we see some more 1-bit registers. I don't know really what they are. The unimplemented instructions gave a timeout for my search operation. So the 1 I shifted in never actually propagated to the TDO. So this is a chip where the unimplemented functionality, unimplemented instruction registers are implemented in a way that TDO is constant 0. So it's not a real shift register anymore, so you will never get your output, your shift data to the output. But I could find which instructions are actually unimplemented. Most of them are, like 25 of the 32. But there are 3 interesting ones at 8, 9, and 10. There are 2 32-bit registers, which is always nice to see for me as a software guy, because I like 32-bit registers more than like 27-bit registers, because, well, the things I usually care about are software things, and they are usually like a power of 2 number of bits. And I played around with these bits and checked if one, so I figured out that the instruction number 8 is actually read-write, and the instruction number 9 is actually read-only, so it never changed. And the instruction 10 actually does something, so I could provoke some action on the chip. And what I found out after like a day was that this is actually a busmaster access port. So the thing was an SoC, so there were a CPU on it and some peripherals and stuff like that. So it has an internal bus, and we see the CPU has access to this bus. It can read and write memory, right? And there are other peripherals like a DMA engine, which can do the same. And then there's all the busmaster access from the tab. Tab means test access port, so it's just another word for JTAG port. So there's a way to access that bus from the JTAG. And I found out that I have to push in the address I want to read from into the register 8, and then I have to toggle some bits in the register 10, and then the data that was read from the bus would be in register 9. And this is pretty cool because I could access all the peripherals on the chip without affecting the CPU operation in any way. And I could do this by just connecting like 5 wires to the board instead of like connecting 32 wires or tapping a huge bus or something. Or I could even access the CPU internal peripherals that way, like the CPU is doing, just while the CPU is running, so I don't have to run my own code on it or something. The interesting thing on this chip is that it actually has boundary scan documented as a JTAG operation mode, because you need that for manufacturing. And it has a JTAG cell pin, which wasn't documented, but it was documented as it must be connected to ground. And when I did a chip map of that chip, when JTAG cell was tied to 0, the chip JTAG space looked completely different. Like the IR length was different, and there were completely other registers, and in fact, the only valid operation was the boundary scan, which I wasn't so interested in. But then I tried to put the JTAG style pin to the invalid combination, and well, it changed completely, and I found this busmaster port in the JTAG space. So when you're interested in test modes, always do the different thing that's documented in the datasheet. So if there's a pin which must be tied to ground, put it too high. And sometimes pins are labeled as TM something, which means test mode something. Those pins are interesting. Try all combinations. If there are 3 of them, try all 8 combinations. And always observe what changes, like if the JTAG space changed. Maybe sometimes, for example, the CPU wouldn't execute anymore, but wait in some test mode. Well, that might be fine, because you could probably still do what you want without the CPU executing code. Just play around with the chip and try to see what different modes the chip can be brought into. Sometimes the pins are just labeled as reserve. I mean, there's always a chance that you fry the board or the CPU by doing that, but I never actually fried a CPU by like pulling some reserve pins to different levels. So be careful, but try to experiment with it, and it's well worth it. And yeah, so the conclusion on this chip is that we found a bus master access to the local bus in a pretty convenient way, because it's just attaching a few wires to it. And we don't have to run code on the CPU, or we don't have to like, do other like code injection or whatever. We can just use the JTAG port to access everything the CPU could do, including memory, including peripherals. So yeah, the last part, JTAG obviously kicks butt. And the chip designers should be aware of that, right? Because they know what test mode function is actually present in their chips. So aren't they aware that hackers might use that for like compromising security? Some of them are, but surprisingly many aren't. So for a software guy, it's pretty normal to have the security mindset, right? We look at software and we need to fix it against like network attacks and something. For hardware developers, some hardware developers have this mindset as well, but surprisingly many don't even want to know something about security, because they care about functionality and they care about time to market and costs and all of that, but they don't care much about security. So it's a completely different scenario than what we know these days from software development, where security is really a core part in the design. Of course, it's different. There are some high security chips and their designers care well for security, but for general purpose chips, like a South bridge in a PC, the designer probably didn't have thought of security at all. I mean, why should they? And hackers can use that to get like read out keys from memory in a PC by attaching to the JTAG port on the South bridge, for example. And well, still, even if the designers thought about security, they still need their debug functionality, because even they need to debug their chips, and they cannot afford a security-only chip spin just to remove the debug functionality. So one countermeasure is that chips disable JTAG either completely or just several instructions in a configuration that is shipped. So they have separate configurations for developers and the end product. And one way this could be implemented is a software-accessible JTAG enable register. And with the software which runs on the device determines that while I'm a development device, it will flip a bit and will enable JTAG operation. So this is, for example, the LPC22XX series implements something like that. And when I looked around on the internet, I found this quote. So the user manual for the LPC clearly states that upon reset, JTAG debugging is disabled by default, and that it is enabled by the bootloader only if the code read protection feature is not enabled. Which sounds great. I mean, the bootloader could determine if in software, it could read in Flash and see if the chip is unlocked or not, and then enabled or not. However, what he found was that by looking at the bootloader, which is provided by the vendor, that the first thing the bootloader does is to actually disable the JTAG debug port. And this is done both for hardware and watchdog resets. So the question is, why do they disable the debug port right after reset, right in the first few instructions, if it's already disabled? And a good question to ask is always, if JTAG is disabled by default, how is the initial boot code written to a device? I mean, there must be a way to access that flash. And while I don't know for sure, but I would be suspicious if I would had to use that chip in a secure environment, because I really would want to know if JTAG is disabled or not when the chip powers up before executing any code. Because it's always better to rely on security to implement security by relying on something not failing, like relying on the bootloader to disable JTAG. It's easy to make a chip failing, for example, by glitching or by other methods. So it's always easy to make something fail. It's much more harder to make something failing to not fail. So you should not rely on security by having boot code which actively disables the JTAG interface. It should be always default. So this is a second method that is implemented, which is a bit stronger, where E-fuses or flash cells are used in a one-time programmable mode. So you have a bit you can set. I think most microcontroller programmers of you know, for example, those fuse bits in most microcontrollers. You can set that after programming, and it will like disable Jtag. And you can do this in waiver testing or in product manufacturing or where you want. And an optional extension of this is a secret unlock sequence you can run through to re-enable Jtag if you really need to do debugging in field. The problem is that asymmetric operations like RSA are usually not feasible to implement into hardware, so they're usually doing symmetric challenges, and they are really hard to make secure against replay attacks because you need a good random generator and you need some good encryption and all of that. So be careful with chips that implement Jtag unlock by doing some secret things, even if there's a hard secret like a key embedded into the device. The question is again always, how are those security bits being programmed? And the answer is usually over the debug bus. So the conclusion is that the debug bus is when the device just exits the factory, it's still in a debug mode, so every debug functionality is still accessible, and it will be locked down more and more when it leaves the factory. So the initial production state is usually the most insecure device state, which is, sounds pretty good. It would be bad if it would be the other way around. But the question is, how one-time programmable is one-time programmable really? So, for example, flash-based OTP, you can mess around that with strong UV light, like you erase an EEPROM. You can apply the same technique to a chip. Or E-fuse-based OTP, where you physically blow a fuse on the silicon, sounds pretty secure, but actually it's not that you blow a fuse and it makes pop and there's a small hole in your silicon. In fact, all you're doing is like changing the resistance of some element on your chip and hoping that the resistance is high enough that this is actually sensed as a blown fuse versus a non-blown fuse. So for e-fuses, sensing e-fuses in a correct way is rocket science, and it's very important to have the proper reference supply. So what vendors usually implement is a low voltage lockout, so it won't boot up at all if the voltage isn't enough to reliably read e-fuses, but not all of them do. Another interesting thing is some chips have a very strict power sequence requirement, like if you have like a core voltage and an I/O voltage and another core voltage and something. It's very important, and the datasheet says you need to apply them in the right order. And if you don't do this, bad things will happen. But what usually nobody can tell you exactly is what will happen if you do that. And even most hardware designers can't tell you really. They can tell you it's out of specs, but it's hard to tell what actually happens. And you should definitely try what happens, especially to sensing fuses. And I have seen some part failing at sensing fuses if you apply voltages in the wrong order. It would sense all fuses as being 0. And this is the default state after production, so it's the most insecure state. So if you want to re-enable Jtag on a device where the Jtag, it is not really a fuse there, but some flash thing. If you would want to re-enable Jtag, you would have to set up a wrong power sequencing, and it will come up all in insecure mode, and you could use Jtag again. So this is definitely something you need to be aware of, that having an e-fuse doesn't mean that the e-fuse actually works in every combination, and that the hacker isn't able to make the environment bad enough that the e-fuse might fail. So, yeah. So that's actually most of it. I hope you got a good understanding on what you can do with Jtag. Jtag should be considered as a tool for people, so you should be aware what you can actually do with that tool. So if you have built some hardware with some chips on it and you don't have much documentation about it, try to see what you can do over Jtag. Try to find the hidden test modes. And by doing the algorithms I've presented here, I think you are able to like map the Jtag space and see if there are hidden test modes in it. You might not find all, but there are usually a lot of them. And be sure that the manufacturer of your chips tell you all about the security implementation of these test modes. vendors are usually quite shy about telling things, because if you have a chip that can be locked down, the vendor still usually wants to have a way to find out what failed if a lockdown chip failed. So they sometimes have test modes which can unlock a chip or run some test pattern even on a locked chip. And you should definitely be aware of that those test modes exist, and get the right input from your vendor, and be sure that the vendor is not hiding stuff from you, because it affects the security of your hardware and your secrets. Okay.
If there are any questions, please come to the microphones and the else. Yeah, go ahead.
My question is, do you know about some people who use power glitching in order to disable the Jtag disabling in the beginning of the boot process?
Sorry, can you speak a bit louder?
Yeah,
I'm sorry.
Do you know if some people use power glitching in order to skip the instructions that disable the Jtag disabling function in the beginning of the boot process?
Yeah, so using voltage glitching to skip that instruction is definitely a possibility. So this is another way why you should not rely on your code disabling Jtag.
Exactly. Yeah.
So, and yes, I think that's also how some people have been successfully able to read out those LPC microcontrollers.
Okay, thank you.
Okay, I don't see any more questions, so thank you very much.